Hello everybody, my name is eMoney SAD. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 19. In this chapter, we're going to discuss reactions and properties of aldehydes and ketones. And you know what? Let's start off by drawing a ketone and an aldehyde so that we can visually remember how similar they are. All right, so here we have our aldehyde. And here we have our ketone, and we're going to go ahead and label them aldehyde and ketone. All right. Both classes of compounds, both aldehydes and ketones, possess this carbon double bonded to an oxygen. Here's our carbon double bonded to an oxygen in our aldehyde, and our carbon double bonded to our oxygen in a ketone. This group is called a carbonyl group, and both ketones and aldehydes have this carbonyl group. The difference really is that the carbonyl group of an aldehyde has this hydrogen group flanked on it, while the carbonyl group has two variable groups, two carbon atoms on both sides. Now, in this chapter, we're going to cover three big topics that are going to revolve around aldehydes and ketones. We're going to talk about how to prepare aldehydes and ketones, and this will predominantly be a review of a lot of material you've covered in previous chapters. And then second, we're going to talk about nucleophilic addition reactions that can occur with aldehydes and ketones. And lastly, after we cover all of that, we can then talk about synthesis and synthesis strategies. Now, of course, first topic, preparation of ketones and aldehydes. Let's pause and review this material. This was taught in several different scattered chapters in what should have been Organic Chemistry 1, but if you've forgotten, worry not, right? We're going to review this now, and we're going to start with aldehyde preparation. Okay, there are several ways we can prepare aldehyde. We can prepare aldehydes through the oxidation of primary alcohols. All right, so for this, when treated with a strong oxidizing reaction, what happens is that the primary alcohols are going to be oxidized to carboxylic acids. All right, any one of these reagents listed here, all right, any one of these reagents will accomplish this, as they will not further oxidize the aldehyde. All right, so if you're starting with a primary alcohol like this one listed here, all right, you can use any of these reagents to oxidize it into a carboxylic acid. All right, this carboxylic acid has this carbonyl group we're talking about with a hydrogen on one side. All right, this is our aldehyde. All right, yes, it's a carboxylic acid. Carboxylic acid's aldehyde here. All right, fantastic. Another way we can prepare aldehydes is through the ozonolysis of alkenes. This is another way to prepare aldehydes. Remember, ozonolysis will cleave, all right, kind of like cut through a carbon-carbon double bond. And with this example, what we form at the ends are aldehydes because there's the presence of these hydrogen groups on both sides of the double bond. So we have our alkene, right, this double bond. Okay, and on each side of the double bond, this carbon is attached to a one hydrogen. And that means when we use our little molecule scissors here to cleave this via ozonolysis with these reagents, what we actually form are two aldehydes because each carbon had one hydrogen. Fantastic. Lastly, another aldehyde preparation method is hydroboration oxidation of specifically terminal alkenes. So these are triple bonds where they have one variable group on one side and a hydrogen on the other. Now, if you remember with our hydration addition reactions from chapter 8, this reaction proceeds via anti-mark addition of water across that pi bond. And this is going to be followed by tautomerization of the resulting enol to form an aldehyde. And don't worry, guys, we're going to refresh on tautomerization in case you've forgotten what that mechanism, what that process entails. Okay, we're going to get into that later on. But just remember, hydroboration oxidation of terminal alkenes, all right, using these reagents can result in an aldehyde. Now, for ketone preparation, we can prepare ketones through oxidation of secondary alcohols. Any one of these reagents, well, actually there's one set of reagent that is shown in this diagram, but this reagent will accomplish this and it will not further oxidize the ketone you get. All right, we can also prepare ketones through ozonolysis of alkenes that do not have any hydrogens at the carbon sites here. So as you see, carbon on one side of the double bond only has R, or variable groups, if you will. No hydrogens there, no hydrogens there. So when we take our molecular scissors, all right, and we cleave this double bond through ozonolysis with these reagents, what we form are these two ketones. All right. Now, in addition, acid catalyzed hydration of terminal alkenes can form ketones. Why? Because this procedure, if you remember from chapter 8, again, proceeds via mark addition of water that is going to be followed by tautomerization to form a ketone. And again, don't worry if you do not remember what tautomerization is. We will go over this in this chapter anyways. And last but not least, we also have Friedel-Crafts acylation, all right, where we can add a ketone to an aromatic ring to produce an aryl ketone. And we just covered this already, this mechanism, in Organic Chemistry 2 already, and we have a video about this if you want to refresh your mind on Friedel-Crafts acylation. All right, now, the mechanisms of all these reactions, like I said previously, were the focus of prior chapters that you have covered in your organic chemistry journey. All right, so if you care to refresh your memory, you can always reference my videos for these chapters, right? Each one of these mechanisms lists the chapter where you can find more details on. And if you don't want to use your textbook, you can always reference my videos. If you don't want to use my videos, you can always reference your textbook to familiarize with yourself or to refresh your memory of the mechanisms for these preparation methods of aldehydes and ketones. But really, we don't need to focus too much about the mechanism right now to get us through this chapter, all right? So let's just do some quick practice problems just to make sure, all right, that we got this. We know how to prepare ketones and aldehydes, all right? We're going to look at A right here. All right, we need to identify the reagents that can be used to achieve each of the following transformations, all right? So we're going from this to this, all right? So the first thing we want to identify, all right, is what kind of alcohol is this? Is this a primary alcohol or a secondary alcohol? Well, we're starting with a secondary alcohol, all right? The carbon that's directly attached to the oxygen has two groups attached to it, right? Two groups attached to it. It's a secondary alcohol, and we are trying to convert this secondary alcohol into this ketone group here. All right, we know the way to do this. All right, we're going to scroll right back up, right? Oxidation of secondary alcohols to get us a ketone. Easy peasy. All right, we need sodium chromate, sulfuric acid, and water. This will get the job done. So the reagents that we need to achieve this this transformation is sodium chromate, all right, sulfuric acid, and water. Fantastic. All right, now let's look at B right here. All right, what are we starting off with and what are we ending off? Okay, this right here, this is an alcohol again. All right, this alcohol is being converted into an aldehyde. This is a primary alcohol that is going to an aldehyde. All right, what kind of reagents do we need to accomplish this? Easy. Let's scroll back up. Oh, oxidation of primary alcohols to get us to aldehydes. Any one of these list of reagents will do the job. All right, so just the first one, whatever, PCC, all right, and CH2Cl2, all right? That's one reagent that you can use for this reaction, for this preparation of an aldehyde, all right? Any one of these reagents, by the way, all right, will accomplish this task for you. So if you listed any of those or you were thinking about any of those reagents, those are all correct answers for this transformation. All right, now if we look at this third one, this third reactions, all right, we have an alkene right here, a terminal alkene, and what it is being converted to is a ketone. All right, so we're going from an alkene to a ketone. All right, what kind of reagents do we need? Easy peasy, all right? What we're going to do is an acid catalyzed hydration of a terminal alkene. If we have this triple bond, this terminal alkene, and we want to form it into a ketone, what we need to do is go through a acid catalyzed hydration, all right? And the reagents that we need are sulfuric acid, water, and this mercury sulfate. All right, so we're going to go ahead, we're going to write that out. This is the set of reagents that will accomplish this transformation. All right. Fantastic. So now we've gotten a little bit acquainted with these preparation methods, and you can always do more practice problems, seek out more practice problems, just to make sure you familiarize yourself with the reagents that accomplish transformations of starting materials into either aldehydes or ketones. Fantastic. All right, now we want to move into our second big topic of this chapter, and that's nucleophilic addition reactions of ketones and aldehydes. And here, before we get into those nucleophilic addition reactions, we want to stop, all right, and we want to ask what makes, all right, the carbonyl group in these ketones and aldehydes electrophilic, right? Because they need to be electrophilic for these future nucleophilic addition reactions that we're going to learn to happen, all right? And the answer to this lies in the fact that the electrophilicity of a carbonyl group, all right, comes from two main things, all right? The inductive effect of the carbonyl group and resonance, all right? Now, if we look at the resonance structure of this carbonyl group in an aldehyde or a ketone, what you notice is you have this pattern that we saw when we learned about resonance, right? You have a carbon atom attached to a more electronegative atom, all right? A pi bonded to each other. What happens here is this pi bond can actually dump the electrons to the more electronegative atom, which in our case for a carbonyl group is obviously the oxygen. All right, so when we're drawing the resonance effects, the resonance structures of a ketone or aldehyde, all right, the double bond can dump its electrons on the oxygen, generating this negative charge at the oxygen and this positive charge on the carbon, this positive charge on the carbon. All right, this is one of the sources of this electrophilic property of the carbon. In addition to inductive effects, where obviously our oxygen is more electronegative than our carbon, resulting in a partially positive charge on our carbon, a partially negative charge on our oxygen. So this inductive effect also renders the carbon atom deficient in electron density, just as we have seen in the resonance structure. So therefore, right, this carbon is particularly electrophilic, and that means it's going to be susceptible to be attacked by a nucleophile that comes around. All right, now the second question we want to ask, well, okay, cool. This carbonyl group in aldehydes and ketones, the carbon is very electrophilic. It's going to be attacked by nucleophiles. But hey, are aldehydes or ketones more reactive, right? And the answer is aldehydes. All right, why? Well, this observation can actually be explained in two ways: steric effects and electronic effects. So in regards to sterics, well, obviously a ketone's going to have two alkyl groups that are going to contribute to steric interaction in that transition state when the nucleophile attacks. Whereas an aldehyde really only has one alkyl group that's going to get in the way when a nucleophile wants to attack our electrophilic carbon. So not that much in the way of the nucleophile attacking the carbon. All right, so that's one consideration, right? The sterics. The ketone has kind of like two bodyguards around the electrophilic carbon, whereas the aldehyde really only has one bodyguard around the electrophilic carbon. So obviously, the aldehyde's more susceptible to attacks. All right, so that's one way of thinking about it. Now, the other way of thinking about it is electronic effects, all right? Recall alkyl groups, right? The things that are going to be attached, the alkyl groups are electron donating, right? So a ketone is going to have two alkyl groups. It's going to have two electron donating alkyl groups that can potentially stabilize that partial positive on the carbon atom of the carbonyl. In contrast to aldehydes, which are only going to have one alkyl group, one electron donating group. All right, so that partial positive charge of the aldehyde is going to be a little less stabilized than that ketone. And as a result, aldehydes are going to be more electrophilic than ketones and therefore more reactive. Now, ketones and aldehydes both can react with a wide variety of nucleophiles. Some will require basic conditions and others are gonna require acidic conditions. And a good portion of this chapter is gonna be us focusing on and studying how nucleophiles from oxygen to sulfur to nitrogen, hydrogen, and carbon, how those are gonna react with ketones and aldehydes, all right? So we're gonna go ahead and we're gonna start with our first nucleophile. We're gonna talk about oxygen nucleophiles, all right? So we know that nucleophiles can react with all these groups, and we're going to cover how they will react with all these groups, starting off with good old oxygen, all right? Now, first, when an aldehyde or a ketone, all right, when an aldehyde or a ketone is treated with water, all right, that carbonyl group can be converted into a hydrate. That means that carbonyl group gets converted to two alcohol groups instead. All right. Usually, the position of equilibrium is going to generally favor the carbonyl group instead of that hydrate. But we have our ways to enhance the forward reaction. All right. We have ways to make a carbonyl sitting in water move forward and form this hydrate. All right. And we can do this either through acid or base catalyzed reactions. All right. And we're going to explore both ways. All right. So starting off with base catalyzed hydration, we start off with a hydroxide ion. All right. Hydroxide. All right. This is a base, hence why this is called a base catalyzed hydration. All right. This is our nucleophile. All right, look at those electrons just waiting to react and attack an electrophilic site. All right, so this is going to proceed obviously through a nucleophilic attack. All right, where our hydroxide is going to come in and attack that electrophilic carbon of our carbonyl group. All right, and then what happens is a proton transfer. All right, and that proton transfer right here from water is gonna result in this hydrate product that we want. All right, look at how nowhere in this reaction do we form acids. All right, hydroxide is a base. Our water here is obviously acting like a base. We know that water is, has this duality of acting as an acid or a base. Here it's clearly acting like a base. So all we have are just bases, no formation of acids anywhere in this reaction. All right, so this goes back to the fact that it's called base catalyzed hydration. All right, always remember, if you're trying to practice drawing mechanisms, all right, a good way to double check you're doing it right for a base catalyzed reaction is that nowhere in the process you're making acid. All right, now for our acid catalyzed hydration, all right, what we can do is, right, we can start off with our ketone or aldehyde, whatever, okay, and we can treat it with hydronium. All right, hydronium here, all right, is going to be our acid in this case, okay? First step, the carbonyl group is going to be protonated, all right? So this oxygen's going to take that hydrogen from hydronium to form, all right, rendering it more electrophilic, okay? And then this intermediate is then going to be attacked by water, all right? Water here is acting like an acid, okay? It's coming into that electrophilic carbon in our carbonyl, and it's attacking to form an oxonium ion, all right? That's a cation in which the positive charge resides on the oxygen, all right? That's what that is called, okay? Now, this is going to be deprotonated, all right, by water again, to give us our final product. All right, so this is another way to form this hydrate product that we want. Okay, look at this process, this acid catalyzed hydration. Nowhere in the process do we form any bases. All right, that's another good way to check. Whenever you're drawing the mechanism for an acid catalyzed reaction, all right, you can double check that you're doing it right if you do not form any bases, okay? It's just simply acids. We're dealing with acids, hence why it's called acid catalyzed hydration. All right, one more time. Be very careful between base and acid. Note that under acidic conditions, all right, a mechanism will only be reasonable if it avoids the use or formation of strong bases. All right. All right, water is this exception because it acts like both. All right. Under basic conditions, a mechanism will only be reasonable if it avoids the use or formation of strong acids. All right, that makes sense. Keep that in mind. All right, so that is hydrate formation for you. All right, starting off with a ketone or aldehyde, you can treat those with water, all right, through either a base or acid catalyzed hydration to form your hydrate product. So that's one type of reaction with our oxygen nucleophiles. Another oxygen nucleophile reaction is that of acetal formation. Here, an alcohol is going to attack a aldehyde or ketone under acidic conditions. All right, so in acidic conditions, an aldehyde or ketone is going to react with two molecules of alcohol to form an acetal, and this is an acetal right here. All right, it's these oxygen groups that also have R groups attached to it. So it's kind of like these little ethers that you form here. All right, so this is a acetal right here. All right, so again, in acidic conditions, right, our aldehyde or ketone is going to react with two molecules of alcohol, all right, to form an acetal right here. All right, it works with an acid catalyst because this is what's needed to protonate the carbonyl group first, and then that renders the carbon atom, guess what, more electrophilic for the following nucleophilic attack. And let's take a closer look at this mechanism. All right, let's discuss some of these really important steps. Make sure you really familiarize yourself with this reaction for future exams. I know that in free response problems when I was in organic chemistry, we had to sometimes draw full out mechanisms for certain reactions. You might need to do that, so make sure you practice this, all right? But let's talk about it, because talking about it is really going to help us understand what's going on, and that'll make remembering the mechanism a lot easier. All right, so the first three steps of acetal formation, all right, produce this intermediate called a hemiacetal, all right, like a half acetal, right? We know our acetal group has these two OR groups, right, where R can be some variable group, some alkyl group attached to the oxygen, right? In our first three steps, we add only one of these OR groups, all right? All right, those are the first three steps that leads us to a half acetal, a hemiacetal, all right? Notice what we have. We have a proton transfer. All right, that's our first step. The carbonyl group is protonated. That makes this carbon a lot more electrophilic so that this group can come in and attack, this nucleophile can come in and attack that electrophilic carbon. All right, and then we do one more proton transfer to form our intermediate, our main intermediate here, this hemiacetal, this half acetal, if you like to think about it. Notice, all right, the acid is not consumed in this process. Now, the last four steps of this mechanism essentially take this hemiacetal and convert it into an acetal product, all right? These four steps involve a proton transfer, right, where the OH group is protonated and thereby converting it into an excellent leaving group. Then that is followed by loss of a leaving group, all right, and then a nucleophilic attack followed by one final proton transfer to get our product, our acetal product. All right, now it's really important. Sometimes when people are practicing the mechanism for this, they kind of combine these two processes together, all right, and they just kind of draw it combined, where the loss of a leaving group happens and right immediately the nucleophilic group attacks. That's not really what happens. All right, the leaving group legitimately leaves first to form this resonance stable intermediate that is then attacked by nucleophile in a separate step. That doesn't happen in a concerted process. So please be careful with that whenever you're learning and memorizing to draw this mechanism, that those are different steps. You draw the loss of a leaving group, then you draw a nucleophilic attack in two different steps, not in one concerted process. All right, aldehydes favor the acetal formation, all right, quite a lot. Ketones usually prefer reactants. This can be altered usually in actual labs when you're trying to do this through distillation products so that the reaction can reach completion. But now, fun fact, acetals can also act as protecting groups, which is really cool, right? Because the process is reversible. So if there is a group, all right, say an ester, all right, say an ester that you want to reduce, all right, look at this ester. We want to reduce this, all right? We want to reduce this, but dang it, there's this other carbonyl group here that we don't want anything to happen to. We really just want to reduce our ester. How do we do that without accidentally also reducing the ketone? Well, what we can do is first form an acetal here at that ketone, right? Because at ketones we can form these acetal groups, right? We can transform them, I'm so sorry, into acetal groups, all right, through our reactants, right? The group that we want to attach right here, okay? And then after this acetal is formed, cool, we no longer have a ketone there that we might reduce. We can go ahead and use our reducing agent like lithium aluminum hydride to reduce our ester. Wonderful, look at that, we reduced it. And now what we can do is finally remove this acetal group and go back to having our ketone there. And look at that, we reduced our ester without reducing the ketone. All right, so this is a great technique. This is a great strategy that you might need to use when we start doing synthesis problems. All right, so keep that in mind. All right, remember when we learned about blocking groups? All right, this is kind of like the same functionality or similar enough. All right, so remember, acetals can also act as protecting groups. Fantastic. All right, now you can also go backwards, right? You can start with an acetal and go back to a ketone. All right, the reverse process is called hydrolysis of acetals. All right, same mechanism, but kind of backwards. All right, so if you need to reference this, this is the mechanism for going from acetal to ketone. Now what we really want to do is a few practice problems to make sure that we have conceptually we conceptually understand this. All right, so let's look at this first problem right here. All right, propose an efficient synthesis for each of the following transformations. All right, so we want to go from this, all right, to this. All right, what's the first thing we notice that's different between starting reagent and product? Well, it should be the fact that our product has this added ethyl group, all right, this added ethyl group to the triple bond. Okay, so we want to add this ethyl group to the triple bond. All right, let's remember from chapter 9, all right, when we have a terminal alkyne like we do right here, this triple bond, all right, we can add groups to it, a methyl or an ethyl, all right, whatever it is that you want, a methyl or an ethyl, through the use of these reagents. All right, Na, NH2, all right, followed by the group you want to add. Well, here we want to add an ethyl, and then with an iodide group on that. All right, so if it was a methyl group that we wanted to add, it would be methyl iodide. All right, but here it's an ethyl group, so we're going to write ethyl iodide. All right, so sodium, or this NH2 group, all right, this alkanide ion, all right, followed by whatever group you want to add. And we want to add a ethyl group. All right, fantastic. That's cool. We know that we can do that. All right, the problem is, though, let's look at this starting material. This starting material has a carbonyl group. All right, we know carbonyl groups. The carbon of the carbonyl group is a really good electrophile. And so in the presence of this nucleophilic alkanide ion, what might happen is it might actually react with the carbonyl. All right, and that's not good. So to avoid this undesired reaction, what we can first do, all right, is convert this carbonyl group into an acetal. All right, therefore, it cannot react when we try to add the ethyl group to the triple bond. All right, so now we have a good strategy. Let's try to draw it out. All right, here is our starting material. All right, first thing we want to do is we want to form this, convert this ketone right here, this carbonyl group specifically, into an acetal group. All right, in order to do this, we're going to use this reagent right here, which is going to help us form that acetal group with some water, all right, or some hydrogen plus, all right. All right, this is going to take us to something that looks like this. Beautiful. We have a carbonyl that is now converted into an acetal group, and this acetal is going to act like a protecting group as we add this ethyl group we want to our triple bond. Then we can easily remove it with some hydronium ion and go back to our ketone. All right, so now what we can do is we can actually treat this with our reagents to add our ethyl group. All right, and if you forgot this kind of reaction is possible, all right, make sure you touch up on some of your Organic Chemistry 1 chapters just to familiarize yourself with some old reagents that you learned. All right, now when we do this, guess what? We get to add our ethyl group to our triple bond. Ooh, this keeps zooming in more and more. There we go. Beautiful. Now we want to make sure we can remove our acetal group and go back to our carbonyl to make sure we get the final product we want. And we can just do this with some H3O plus. Beautiful. And that will give us right back our ketone where we started. And now our triple bond has that ethyl group like we wanted. So that's how we want to approach this synthesis problem. All right, I'm going to let you guys attempt to do B and C. If you have any questions, please reach out. Please ask me in the comment section below, and I'll be more than happy to help you think through that. But what we want to do now is 19.11a. All right, and this problem asks, predict the products for each reaction below. All right, so if we have this group right here, this starting reagent, and we treat it with hydronium ion, all right, what is going to happen? Well, this has to do with this acetal formation and hydrolysis of acetal groups that we just talked about. All right, we have this acetal group and we're treating it with H3O plus. Well, obviously what this is going to do is convert, it's going to hydrolysize the acetal group right here. All right, if we have an acetal group and we treat it with H3O plus, it's going to end up giving us back our ketone. All right, so the product that we're going to get for this reaction is going to look like this. All right, and then of course our side reagents, right? Right? Fantastic. All right. So that is how you would approach that problem. Okay, well now, what about, actually, I'll let you do B yourself. All right, and if you have any questions or confusions, again, please ask me. That is what I am here for. Okay, but with that being said, we're actually going to move into, actually, let's do, I guess I have a few more problems for us to do. Let's do these. Draw the products that are expected for each of the following reactions. Okay, so again, similar to what we just did, here's an acetyl group. All right, what if we treat it with hydronium ion? Obviously, it's going to hydrolysize the acetyl and it's going to give us back our ketone. Actually, this is pretty similar. Oops. Very similar to the one that we just did. All right, so it gives us back our ketone. This group is converted into that carbonyl group. Now, what if there's a nitrogen there? What happens in that case? Well, again, first of all, for A, not only do you get your ketone, but this acetyl group leaves, which, by the way, looks like this, just like it is removed, but of course, the oxygens have hydrogens. All right, that's for A. Now, for B, again, all right, we're hydrolyzing. We're doing the hydrolysis of this group right here. What happens in this case is, all right, this is actually an oxygen, all right, and your byproduct is this nitrogen with a methyl group, all right, and 2 hydrogens. All right, so kind of the similar process, but instead, look, we changed the oxygen. All right, fantastic. Now what we want to work on are move on to our sulfur nucleophiles. Now, the reactions with sulfur nucleophiles reacting with ketones and aldehydes is actually very similar to what we have just seen with oxygen nucleophiles. All right, and the first reaction we will see is where an aldehyde or a ketone will react with 2 equivalents of a thiol to form a thioacetal under acidic conditions. So you can have a ketone or an aldehyde, all right, it's going to react with 2 equivalents of what this is called as thiol, all right, and what it's going to form as a product is this thioacetal, all right, which is very comparable to our acetal that we formed using our oxygen nucleophiles. All right, and this transformation actually proceeds via a mechanism that is directly analogous to our acetal formation. The only difference really here is our sulfur atoms are taking the place of our oxygen atoms. And just looking at the mechanism here, our first 3 steps are the same. Proton transfer, nucleophilic attack, then proton transfer, resulting in the intermediate of hemiacetal, right? Half an acetal, all right? All right, and then our last 4 steps to give us our final thioacetal is proton transfer, loss of a leaving group, followed by a nucleophilic attack and a proton transfer to give us our final product. Now, fun fact, extra fun fact actually, thioacetals can also act as protecting groups, just like we talked about with acetals. Thioacetal formation is a reversible process, and that can literally be controlled by just choosing your reagents and conditions carefully. And this is very similar to what we just talked about. All right, the only difference here, right, we can use this as a protecting group. The way that you go from a thioacetal back to a ketone or aldehyde analogous to that what we just covered. Now, a cool thing is if you take your thioacetal, all right, and then you introduce Raney nickel, all right, what you can do is actually reduce the carbon. So that's also a very interesting thing to keep in mind, especially when you get to slightly complicated synthesis questions where you have to be a little bit strategic. This might prove to be advantageous for you to remember in regards to solving problems like that. All right, and what we're going to do here is actually do a few practice problems in regards to this. This question asks, predict the major product for each of the following reactions. Okay, so first and foremost here we have a ketone, all right, and our first step here, number 1, obviously we're going to treat it to 2 equivalents, actually, kind of, you can think about it like that, of thiol, and we're going to treat that with a ketone, and what we're going to form is a thioacetal here. So that's our first step, all right, for A. Those first set of reagents are going to help us form our thioacetal, all right, so what's going to happen, all right, is we have this, all right, and what happens to our ketone here, all right, what happens to our ketone is it's no longer a ketone, but instead we're gonna form a thioacetal, All right, that's cyclic because of the kind of reagent we're starting off with. We saw the same thing with our oxygen nucleophiles. All right, so you know how to do this. Now, we have an extra step here, all right, where we treat it with rainy nickel. All right, remember we just talked about this. Rainy nickel takes this cyclic thioacetal, all right, it's gonna reduce it. What that means is this all goes away and we just have hydrogens there instead. This is going to be replaced by hydrogens. And so actually, our final product is going to look like this. All right, so once again, all right, our first step, we treat it with a thiol. So our ketone gets converted into a thioacetal. All right, this is analogous to what we just saw with our oxygen nucleophiles, except now we're dealing with sulfur. All right, now there was one more step here, and that was treating it with rainy nickel. Rainy nickel is going to reduce, all right, our thioacetal, and what we have there instead are just hydrogens. Okay, let's do one more. Let's do B. All right, first step is, again, we have this aldehyde. All right, we have this aldehyde that we are going to treat with a thiol. All right, so we know what this is going to look like. All right, we have our thioacetal that forms. But again, we have one more step, this rainy nickel that we are going to treat this with. All right, what this is going to result in is this carbon right here with the thioacetal group. That thioacetal group is going to be converted into hydrogens. All right, so we're just going to reduce that carbon site. All right, so what our product actually will look like is, well, now we have all three hydrogens. All right, so that turns into just a complete methyl group, and this is our final product. All right, so this is going to wrap up the first half of chapter 19. In the second lecture, we're going to continue chapter 19 by talking about nitrogen nucleophiles, carbon nucleophiles, and hydrogen nucleophiles. And that will wrap up the rest of chapter 19. I hope this video was helpful. If you have any questions about the problems we did together, or you want to see more, you want to do more of these kinds of problems, send me your questions. I can always make extra videos where we simply do more problem sets. I'm more than happy to do that and accommodate that for you. Other than that, good luck, happy studying, and have a great day.